Alright, so we're going to start with beats. So we already looked at noise-canceling headphones, or the example of waves that are interfering, and we saw that if waves interfere constructively, and we have two different waves, constructive interference means that the troughs line up with the troughs and the crests line up with the crests, so that at any given point, the two amplitudes add together. So this is the opposite of noise-canceling headphones, because this would make a bigger amplitude, a louder noise, and noise-canceling headphones are the opposite. So for those, what was that? This would be constructive interference. So constructive interference means the two waves build off of each other and help each other. So they're adding together to make a bigger amplitude, a louder noise if you're talking about sound. And we're just drawing sound waves like this, even though we now know that they don't look like this, but it's an easy way to draw waves. So destructive interference is where at any given point, your two waves, when they add up, will cancel each other out. So a positive amplitude and a negative amplitude will end up with 0. Here's your noise-canceling headphones. This is destructive interference.
So when they're together, it makes the frequency more, or the amplitude?
The amplitude. Because the amplitude of a wave is connected to the volume, and you can tell that because the wavelength or the frequency is just how far apart they are. That's not going to change. Like the two wavelengths are the same, so they don't add together. They're just the same thing. But the amplitudes are different, so they're going to either add together or cancel out for constructive or destructive. Now, we are not always going to encounter waves that line up perfectly and have the same wavelength. So if we have this situation, but one of the waves has a different wavelength, in other words, these waves don't line up on top of each other, they're slightly offset. So one of them is a little bit to the side, and then it'll keep being offset as you go along. That's something that produces what we call beats. So beats is when two waves with different frequencies. So noise-canceling headphones or fully constructive interference, they have the same frequency and same wavelength, so it's the same distance, takes the same frequency or same period. So the two waves with different frequencies interfere, and that's what we call beats. So let's say the best example of this is you will, if you're tuning a piano, you will try to tune it to whatever frequency the note is. Does anyone happen to know what the frequency of the A above middle C? I doubt it. Even the music people, like there's probably people who could sing or play the A above middle C, but
play it is easy enough. You just got
I think it's 440. All right. So let's say you're trying to hit that A. This is the A above. So that A is 440 hertz. So that is the frequency. Where did my purple go? Oh, my purple. All right, this is the frequency that we would want to hit if we're tuning a piano. So this is the frequency. So we're gonna use a tuning fork. If you use a tuning fork, the frequency of your tuning fork is exactly equal to 440 hertz. And that doesn't change. But what'll happen if your piano is out of tune, if you hit the tuning fork and then hit your piano key, you'll hear or you'll pick up a frequency that is equal to the difference between your actual tuning fork or what you want and wherever your piano's at. So there's an equation that we use that says the frequency of a beat is equal to the absolute value of frequency 1 minus frequency 2. And this is the only equation that there is for beats. It's fairly simple and straightforward. This just says if two waves are interacting or interfering with each other, like a tuning fork and a piano key, and one of them is different from the other, the frequency of the beat that is produced is just the absolute value of the difference between them. So in this example, we could say we observe a beat frequency of 3 hertz. And so if I ask you, what would the frequency of the piano key be? What should our frequency, yeah, Brendan?
Couldn't it be 443 or 437?
Yes, it could. So Brendan says it could be 443 or it could be 437 because of these absolute value sums. So we can get 3 hertz for the frequency of beat either by it being 3 hertz too high or 3 hertz too low. So on the surface, there's no way of telling in this. I mean, if you had a well-trained ear, you could tell. But if we only know that the beat frequency is 3 hertz, we can't know if it's 443 or if it's 437. So we're going to assume in this case that it's too high, and it's 443. So this, you would get 443 minus 440, or 440 minus 443, and you'd get 3 hertz. Yeah, put it.
So, to recap the meaning behind the frequency beat, is it just that on the board that
Yep.
2 waves? Okay.
Yep, so F1 and F2 are our 2 waves. They have 2 different frequencies, F1 and F2, and they interfere with each other. So you're hearing both waves at once if you're talking sound. If you're not talking sound, they just interfere with each other. And the beat frequency of the resultant wave is the absolute value of the difference between them. So you're gonna get that frequency, and it's weird, like you can kind of hear, if you've ever actually done this, if you take a tuning fork and you have an out of tune instrument, if you hit the string or the key and then hit the tuning fork, you'll hear the notes and they'll be slightly off, but you'll also actually hear this beat that, like, I should really get a video of this, but I'll see if you've never used them. Yeah, I haven't either, because now we have tuners, so we don't have to use tuning forks, so they're a bit outdated. But if you were to do this, and I'll see if we can find a video at some point, but you're gonna hear a beat when you look at the difference between like a tuning fork sound and an out of key piano key. One other thing we can do with this, let's say that we want to get this piano in tune and it's too high. Now music people could probably tell us, if I have a frequency or tone that is too high, do I need to tighten or loosen the piano string? Yep, so we know intuitively or from practice that we need to loosen the string to lower the tone. Now let's prove it with physics. All right.
Okay, well, you're like the only person I know that needs grace. What do you
So we're going to start with our wave equation. If my frequency is too high, this is too high and I want to lower it, I know that a wave on a string, like a piano or a guitar or violin, is equal to the square root of force of tension divided by mu. This was an equation we had before. It just says how tightly you stretch the string and the amount of mass density, how big the string is, how much mass it has, determines the speed of the wave on a string. So if I'd like to lower my frequency, what do I need to do in terms of velocity? Do I need to make my velocity higher or velocity lower? If we want to lower F, we need to also lower V because they're directly related. So we'll check with our equation up here. In order to lower the velocity of the wave on a string, we need to make force of tension smaller and we need to loosen the string. Checks out. Physics and real life confirmed. So just like you view music people would expect. If something is too high, you need to loosen the string. If it's too low, you need to increase the tension, increase the velocity. Your frequency will go up. You'll hear a higher pitch.
So to lower velocity of a wave on a string, you loosen the string.
Yep, if we make tension lower, velocity will go down and frequency will go down. If we make tension higher and tighten the string, velocity will go up and your frequency will go up and you'll hear a higher note. So the two things that amplitude of waves is related to volume for sound, and frequency of waves is related to pitch for sound. Those aren't like...
If tension is higher than velocity.
Yeah, if we increase tension, force of tension, we increase velocity, and if we increase velocity, we increase frequency. Yeah, Brennan.
What does mu mean in this equation again?
This mu is mass density, which we talked about a couple class periods ago, I think. Mass density is just how much mass is in a certain length of the string. So it's like a guitar string versus a tow cable. A tow cable has high mass density. A guitar string has low mass density.
I know that this is being stupid, but what's the thing with the frequency?
This? Lambda, the wavelength. It is weird. It's a weird symbol. Upside down Y. Yeah, lambda is wavelength. So you're not changing, in this situation, when you're loosening the string, you're not changing the wavelength of the sound wave, or the wave on the string, but you're changing the velocity so you can change the frequency. All right, what else? I think that's it for beats. All right, that is all for beats.